Hi everyone. In this series, we'll go through the steps to create a chain of thought LLM that is capable of mathematical and medical reasoning. Further, the model is equipped with RAG, Retrieval Augmented Generation, and do calling capabilities. For training, I will build upon Qwen 2.5 3 billion instruct model and train it in two major steps. The first step is to apply reinforcement learning on a mass dataset to enhance the model capability to reason with mathematics. The second step is to fine-tune the model with a medical chain of thought dataset. The chain of thought dataset is in fact generated by DeepSeek. For inference, the model will be equipped with RAG and agentic capability, which is to call built-in tools. In this particular video, I will go through the step to create a chain of thought model that is capable of mathematical reasoning. And the method that I use is reinforcement learning with group relative optimization policies, or GRPO in short. First, I will go through the theory of GRPO, helping you understand what it is and how it helps us create a chain of thought model. For those who are not interested in technical details, you can skip to the next part. I will switch to the paper by DeepSeek. I'm very impressed by this paper and have learned a lot about it, so I would like to share my understanding about GRPO. Here is the paper by DeepSeek, and this is the part about GRPO. Group relative policy optimization is basically a way to optimize the model's parameter so that it optimizes the type of output that the user wants the model to have. And looking into more detail here, let's say our dataset have a bunch of questions. For each question Q, the model sample a list of outputs O1 up to OG from the original parameters. So the O model is denoted by pi theta O, and here theta O is the O parameters, which are parameters before update. So you can view this O policy simply as the O model. We want to update theta O to theta, so we get the new model by theta. And the way to do so is to update so that we maximize some functions. And this is called the reward functions. Well, in the vanilla training of LLM, the loss function is simply the comparison between the generated tokens versus the crowd truth tokens. In this case, we are not going to optimize loss functions, but the function that we aim to optimize is the reward functions. Before diving into the details, let me make some the notation here clear. So one thing that we want to be maybe the most important thing that we want to be clear about is the forward pass and the backward pass when we train the model. So in the forward pass, we use theta O, which is the current parameter of the model, to generate the probabilities for getting the output. So this is pi theta O, a bit small. So this, we compute the probabilities for getting the output OI given the input query Q. We will use the generated output OI, right? And we use them in the backward pass in the way so that we will maximize the reward functions. So at this point, just view this as a function in terms of theta. So here for the backward pass, we will update theta O to theta. So the goal here is to maximize this function. So we use a gradient extent, theta O, so plus alpha times the derivative of the function with respect to theta at the point theta O. And after we update theta, we will use it to compute all the probabilities of getting the output OI using the updated theta. So this is the flow of the model, and let's look at the definition for the parameters Ri. I guess Ri is one of the important parameters. So in this case, Ri's are called rewards for the model, and in our case for this particular project, I have two types of rewards. There are two of them. So R1 is the reward for following the format correctly. So I call it format reward. And the format that I want the model to follow is its answer should be enclosed first in the thing tag. So this is where the model should put its reasoning, and then it will put out the final answer in the answer tag. So if the model's generation follow this format, it will receive the reward score of 1. If not, then the reward score will be 0. The second reward that I want the model to have is accuracy reward. Accuracy reward basically check the model answer in between the answer tag and give it 1 or 0 based on whether the model answer match the crowd choose answers. For example, the question is what is 1 plus 1? If the model output here the number 2 and the crowd choose answer is also 2, then the model get 1 point. If the answer of the model is 3 and the crowd choose answer is 2, then R2 will be equal to 0. So there are two types of rewards that I use for this project. Before we look into these ugly expressions, here let's look at some other definitions. Here we have pi theta OIQ. This is the probability of getting OI for the given query Q. So note that we use Q to denote the query, and the number of queries is equal to the number of data in our dataset. Pi reference OIQ means a reference probability of getting OI given Q. Well, we have a reference model which is the baseline model, and we don't want at the end when we try to optimize our model to maximize this reward, we don't want our model to be too much different from the baseline models. So this baseline model is never changed, so these probabilities are always fixed. Pi O theta I given Q means the probability of getting output OI given the input question Q. And note that this output probabilities is in the current step of the LLM, and at the next step, theta O will be updated to theta. Yeah, it's kind of repeating, right? So pi theta of OI given Q mean probabilities of getting OI given Q after we update theta O. Okay, and now let's look at these ugly looking functions. So this reward function is the expected value taken over all the questions and all the answers of these whole things. First, we have this part about expected value taken over all the question and over all the output OI. So expected value is nothing but the sum, the average sums of all the questions and all the outputs. So this is the sums of the terms which correspond to all the question and all the generated outputs. Each term in this sums has this form, right? So each term in this sum now turns out to be a sum. Each term in the sum here correspond to one output OI. So this is the sums of that correspond to all the outputs. And for each output OI, this sums is the difference between two terms, these terms and these terms. So the second term here is easier to understand. So we will look at the second term first. The second term here is the KL between the updated model and the baseline model or pi reference or baseline policy. So we don't want our updated policy to differ too much from the baseline policy. So we want the difference to be small. Note that we want to maximize this reward function, so we want this to be small, so this makes sense, right? And here is the formula for the KL between the updated policy and the baseline policies. So actually I prefer to say these are models other than policies, because the term policy for me is a bit fancy and it's just easier for me to understand it as model. Sorry. Okay, so the second term here is to make sure that there is not much difference between the updated model and the baseline model. And the first term here, we have minimum of two things. So this is the first things, and this is the second things. Well, for the first things, it is a scalar, which is a fraction here, multiple of AI. If we look at AI here is the normalized reward, right? So based on the formula, it is the normalized reward. It is Ri minus the mean of all the Ri's divided by the standard deviation, so it's a normalized reward. Well, all the AI here are fixed because we define our rewards beforehand. So if we look at this term here, note that we want to maximize the reward, which means we want to maximize these terms. And AI for the given output OI here is known. So we want this fraction to be maximized. And note that the outputs OI here are generated using theta O, and once theta O is updated to theta, we use the new theta to generate OI again. In other words, the outputs OI are generated by theta O but optimized by theta, right? So it makes sense that this fraction should be big because OI here is like randomly generated. You can consider it as randomly generated by theta O, but it will be optimized at theta in the direction of maximizing the reward. So this term should be big. And what about the second terms? The second term here basically to control the amount of variations between pi theta and pi theta O. We want this fraction to be big, but we don't want it to be too big, because when it is too big, then our new model might be too different from the old models. So we want to make sure that pi theta is not too diverse from pi theta O. So we take the minimum of these two terms. In particular, we want the fraction to be big but not too big, and we minus the difference between the updated policy and the baseline policies. So by maximizing these functions, and note that this function is nothing but the sums taken over all the queries and the generated outputs. By maximizing it, we make sure in this case that our updated model, we encourage our updated model to have the format where the answer in this format, and also the final answer is correct. Alright, so that is my understanding on reinforcement learning with GRPO. Next, we will apply this into training our model. First, we will look at the dataset that we use for reinforcement learning. So the dataset that we use in this case is a data from OpenAI, and it is the dataset of Grade School Math 8K. So it contains 8.5 thousand mathematics problems, math word problems, and each of the data here has two views, question and answers. So let's look at one of them. Question is simply the statement of the questions. For answer, it provides a step to get the answer, and also the final answer is given in this tag. So keep in mind, we have two views, question and answer. Question is the statement of the question, and in answer we have the working and also the final answers. So let me go through the code. Here, okay, I'm using lightning.ai for the GPU to train my model. This might take some time for the setup, so maybe let me just use the GitHub repo. So first we need to install some package on Dataset, reinforcement learning, bit and bytes, unslot. So I use unslot to train. For the data, there are a few helper functions. The first one is to extract hash answers, which is the final answers for a particular questions. As you have seen earlier, in the answer field of any data point, there is the final answers which come after this hashtag. Here I define the system prompt and the user prompt. The system prompt simply say or tell the model that you are an expert in solving high school math word problems. The first thing through the reasoning process, step by step in your mind, and then provide the answers. Well, there is some formatting issue here, so this becomes empty. Let me go back to this. Okay, so now this works. For the user prompt, I say that solve the following questions and show your work or reasoning in thinking tags and return the final answer as an integer in answer tag. Well, this is important because I choose a simple case where the final answer is an integer. I can easily verify whether that answer match the ground truth answer or not. So if you look back to the dataset, all the final answers here are integers. Okay, so the next function is used to format any data point. To use GRPO, each data sample needs to have two fields, prompt and answers. So our dataset is given with two fields, question and answers. We will create additional fields for each data point, which is prompt and target. Prompt and target. So first we define prompt. We start with the system prompt. Raw system content is a system prompt. So this is the conversation format. For users, we will use the user prompt and we format the placeholder for question here as the question that is given in the data. We prompt the answers with some starting words, like let me solve this step by step, and we start with the think tag. So this in some way is to help the model to have a good start. It should solve this step by step, start with the think tag. And here we return a dictionary with two fields, prompt and target. Prompt is this whole thing tokenized, and target is the integer, which is the final answer to the given questions. And next, we will apply this format prompt function to the whole data set. So for each data point, it will be appended with two fields, prompt and target. So to train with GRPO, each data sample need to have two fields, prompt and target. Okay. And note that in the original data set, we only have two fields, question and answers. So first, we load the data set, and we map each data point to a new point where it has additional field, prompt and target using this format prompt functions. It's optional. We can remove the redundant columns, which are question and answers, because these columns will not be used for the training later. So it's optional to keep or remove. And here, I also have a helper function to extract the answer from the model in order to verify correctness. Recall that if the model can respond in the correct format, it should put the final answer as an integer between the answer tag. And this helper function is to extract the model final answer in between the answer tag. And then we load the tokenizers. So the model that I use for this project is 2.53 billion parameter model. And here we load the tokenizers, we load the dataset, and we split the dataset into train and test. And now comes to the reward functions. There are two rewards function or two type rewards that we would like to encourage the model. The first one is to encourage the model to have the correct format, and the second one is to encourage the model to get the correct answers. For the format reward functions, the format that we want the answer to respond to is in this format between think and answer tag. So we have completions. We have the target as the ground truth final answers. Completion here is the model generations, and we want to return a list of reward scores. So the list of reward score here will be 1 or 0s for each score. So we loop through all the completions, all the generations and ground truth answers, and we will try to, here is a complex regular expressions, basically to check whether the model respond in the correct format. And here the model should respond in this format, and especially the first part here is quite complex. I basically copy this from some online resource. Yeah, I don't want to give a false citation, so I don't want to mention the resource here because I cannot remember correctly from the top of my mind now. But this first part here say that it start with the think tag, right? And followed by possibly other tag in between, and any other choice of words, and end with the think tag. So basically it say for the first part it must be between think tag. You can have other tags allowed, but not nested think tag. So that means the think tag here can only appear one time. And the second part here is quite clear. The model need to answer in the format of answer tag. We search for all these patterns. If we don't have any match, then the reward could be 0. If we have a match, the reward could be 1. So we have a list of 1 and 0s, which correspond to whether the model regeneration follow the format correctly or not. And the next reward function is called correctness reward functions. For these reward functions, we simply check whether the model generate the final answer which match the ground truth answers. So we extract the final answers from the model generations, and we compare these answers with the crowd truth answers. So if they are the same, or if they differ very small, then they are considered the same, and we put the reward 1, otherwise the reward is 0. So now it remains to load the model and put it into training. Here I use unsloth to train so that it is faster. My personal experience with unsloth is not very good, but I would have no other alternative. Okay. So here we basically load the model using unsloth. So the syntax is fast language model, which is imported from unsloth. Dot from pre-train, we specify the model name. The mark sequence length here is the context window. You can increase it for longer reasoning trace. We load info bit to save the memory. We enable fast inference for fast inference. The GPU memory utilization here is optional. Yeah, you can put it, keep it, or you can leave it to default values. So this is the original models. We don't aim to retrain the whole original model. We only want to fine tune it, and the technique that we use to fine tune it is LoRa. LoRa is a standard fine tuning technique where we basically, for each linear model, we will okay, let me just search a reward. LoRa. Let me just make a search and explain it here. It's easier with the image. So in LoRa, it replaces each of the linear models. Let's say W here has weight D by D by a combinations of the original model with an additional layer, where the additional layer here is comprised of two matrices A and B, usually D by R and R by D, where R is much smaller than D. So in the second part here, you can see the number of parameters is D times R plus R times D, which is 2DR, which will be much smaller than the first part if R is very small compared to D. And here you might be confused because obviously we are adding parameters, so the new model should have more parameters. However, note that we will freeze the original layer and we only keep this additional part for training. So the total number of parameters here in this case could be reduced because we keep the original layer freeze. Let's go back here. So here the layer that we choose to fine tune will be the target modules, which is Q projection, K projection, V projection, O projection, or the projection layer basically. And we choose R equal to 16, and note that in this here you can see R equal to 16. In fact, larger rank means we have more parameters, which means the model is more capable, but it could be slower. And 16 is kind of a standard value. And here we also use gradient checkpointing, and as I said, a random state so that the result can be reproducible. We load this, and the next part is to put everything together and train. Fortunately, GRPO was already is already integrated into TRL, so we can just use it. If not, then we would have to rewrite the function J that I mentioned earlier and then do gradient descent on that function. But it is already integrated, so we can simply use it. For the training arguments here, we use the optimizer to be big AMW 8-bit, and here we specify the parameters. We set quite a small learning rate, well, this part I am also not very sure about, but when we fine-tune large language models, we usually keep the learning rate small. Logging step here is to log the informations after every 4 training steps. We also set BF16 to true so that it will be more accurate. We also enable gradient accumulations for larger batch size. Per device batch size is 2, but we only modify the gradient every 4 times. So that means even though we have limited memory, we still can change for large batch, which is batch size equal to 8. Number of generation here is set to 2. Recall earlier that for each of the input query, we will set G generation O1 up to OG, and in this case, we set 2 generation per input query. You can increase it if you have more memory, but it will take longer to train. And prompt length and completion length here, certainly you can increase if you have good machine. Here I only limit to 400 training steps, 400 step, and each step is two questions, so we train for about 800 questions in the whole dataset. The whole dataset here consists of 8,500 questions, but we only train 10% of it, about 800 questions. And here we initialize the trainer as GRPO trainer. We simply specify the model, the tokenizers, the reward functions. There are 2, correctness reward and format reward, the training arguments, and also the training dataset. And then after that, all we need is to hit trainer.train. So after the training is finished, we want to save the part of the model that was trained. So by saving only the trained parameters, it will save much more space than training the whole model. So we use model.save LoRa. So this is to only save the LoRa parameters. And I also save the tokenizer, even though we never make change to the tokenizer, but I also save it. And after we save, we want to free the model, the trainer, and clear all the cache to free up the memory. And here are the training details. So note that in the training, we aim to maximize the GRPO functions, which is the function that optimize the way the model generates the output so that the reward is optimized. So if you look at the training metric here, the train loss doesn't change because we don't aim to optimize the loss, but we optimize the rewards. Gradually, the reward increase. Well, we start with about 0.4, 0.5, and at the let me just check again. This is the reward. Yeah, sorry, this is the standard deviation of the reward. The reward here start with about 0.7, and when we finish after 400 steps, the reward increase up to 1.5. Okay, it took me, let me see how long to train this. It took me quite some time to train this. Okay, more than 4 hours, so I don't want to hit run again. I don't want to retrain this again. Alright, so now it's time for inference. So in inference, we will load our train model and try to see how it works on some particular data. Well, we also load the fine-tuned model with unslots. Right? So here we need to specify the base model ID. The max sequence length should be the same. Also set fast inference to true. I will need to install the requirement first. Right, let's do some inference. Okay, we load the fine-tuned model. So first we load the base model and the tokenizers. We will apply the save LoRa weights on the base model to get the fine-tuned model. Note that we have saved the LoRa weight on adapter path here. It's a save LoRa weights. So we apply this additional LoRa adapters to the base model. So we do fast language model dot get path model, specify the model, specify R, which is the same rank during training. Target model need to be the same, alpha need to be the same, and same random state. And then we do model.load adapters. So this is to initialize the LoRa weights and then load the save LoRa weights and set the model to evaluation mode. And we also load the tokenizer from the save path. So let me run this. Okay, we specify the base model ID and adapter path. Now we will load it. Yeah, for this model, you will take a GPU with, I believe, 24 GB to be able to do the reinforcement learning. Yeah, you need at least 24 GB. For inference, so, well, here I try to do the inference on some test data, right? So here I import text streamer so that later when the model generate tokens, it will be displayed token by token live. So for this function, I take in data as the data set, which should be the test data. I is the I sample in the test data. If you don't like this way, you can just have an inference on questions, right? So we the model and tokenizer are already loaded. We get the prompt, which is in fact the questions, and target, which is the final answers from the test data. First, we tokenize the questions, right? So we apply the tokenizer on the questions, and we put it to the model's device. But input length here is unnecessary because here we don't need to save the answers. If we need to save the answer, then this could be necessary because we want to crop out the questions. Yeah. But here we only want to see the answers. So with touch.noclass, we will generate. We use model.generate. Here you can adjust the max length, which is the maximum number of output tokens. You can adjust temperature and the top P. Temperature basically control randomness. When the model output, it in fact output the probabilities for getting all the logits, and that probabilities will be scaled by the temperatures. So if you scale by a low temperatures, the output with high probability will be higher, right? So the output with high probabilities will get even higher chance of being picked. So lower temperature will make the model more deterministic, and higher temperature will make the model more random. Top P here means we will take the top logits with probability summing up to, in this case, 0.9. If you set top P equal to 1, that means you take everything. If you set top P equals 0, that means you take nothing. And then do sample 2. We set in streamers to be the text streamers from the tokenizer so that the result will be displayed token by token. And here I also want to print out the target to see, to compare between the model answer and the final answers. so let's see whether this is finished. Yeah, this is finished. The model, the fine-tuned model is loaded. I haven't load the data. Okay, let's just load the data. All right, now let's run the inference. Okay. Okay, so here there is some warning, but I guess it doesn't affect the answers. So system message is you are an expert in solving high school math word problems. You first think through the reasoning step by step in your mind and then provide the answers. Solve the following questions, blah blah blah. Yeah, this is the questions from the test data, which is some question the model never see before. Show your work in thinking task and return the final answer in answer task. So let me solve this step by step. Think through, and then final answer is 55. Yeah, this match target answers. Okay, why not just, this is redundant. Maybe 1000s. Okay, 500, 300. Okay, the model still do correctly. 100. So the model answer is 78 and the final answer is 78. And here you can see the model really output the answer like a chain of talk model, where the reasoning is kept between thinking task and the final answer is kept between the answer tasks. 100. Okay, so this is an example where it fails, right? The model answer is 705 and the final answer is 175. Interesting. 10 maybe. Well, this one is also interesting because the model seems to fail to display some math formulas. So this is supposed to be some latex formulas, but it gets the correct final answers. Okay, so that is also the end of this video. In the next video, we will enhance the model chain of talk reasoning with some medical dataset. So we will do instruction fine-tuning of the model on some medical dataset. Thank you and see you next time.